All right, guys. So this is our last topic on chapter 5. We're going to go over molecular shapes or molecules in 3D. Because so far when we've been doing Lewis structures, right, we've been drawing molecules on two-dimensional board or your piece of paper. But molecules, of course, are three-dimensional. So how should we think about that? First, what I want to recommend for you guys is if you don't have one of these already, I recommend buying these molecular model kits. Just type that into Amazon, and you should be able to get, these kits for about 15 bucks or even cheaper. But they come with like atoms and bonds, and it's just much easier to imagine these molecules if you have the model in front of you. So that's what we're going to be using in order to show you guys the 3D molecules are these this kit. So before we do that though, let's talk about what makes a compound a certain shape. Right? It's actually quite simple. It has only to do with electron-electron repulsion. And that makes sense, right? Because electrons are all negatively charged. So they don't want to be close to each other, which means atoms don't want to be close to each other. And that's why when we were doing Lewis structures, I had instructed you guys to put the surrounding atoms evenly around the central atom as much as possible because they don't want to be crowded, right? And so that's all that dictates the shapes of these molecules, right? And we call these electron groups, which I abbreviate as EG for short. But when you count for electron groups, this is really simple, guys. Let me show you. Anything counts as one electron group. So let's say that you have a single bond, that's considered one electron group. Okay. If you have a double bond, that's also considered one electron group. If you have a triple bond, that's also considered one electron group. And then a lone pair is also considered one electron group. So everything is considered one electron group, right? It's easy. It's, a group of one bond, a group of two bonds, right? It's just a single group. So it goes by that. The shapes of molecules goes by how many electron groups are around it, because all of these electron groups are negatively charged and they're going to want to get away from each other, right? And that's what's going to dictate the shapes of these molecules, right? So let's get to it. It's going to make a lot more sense when we whip out these models. So let's start with the simplest, or the lowest number of electron groups, and yes, the simplest shape as well. So if you have a central atom where you just have two electron groups around it, how is it going to look like, right? If you want to think about electron-electron repulsion, you want these two electron groups as far away from each other as possible around a central atom. So just think about it. How would you want that? How would you put that? Okay, so you might say, well, they should be opposite each other, right? If I just have two things around a central atom, if I put them, opposite each other, they should be as far away from each other as possible. So what is that going to look like? Like this with our model, right? So if I have a central atom, now I have two electron groups, right? Single bond, single bond. Remember, each of these is an electron group. I need to put them as far away from each other as possible, yeah? So even if I try to squish them together like this, eventually, they're just going to spring back, right? Because they repel each other. So even if you force them together, repulsion will just automatically make them this shape, okay? And what shape does that look like, guys? That looks like a line. Okay, so we call that linear. Okay. So let's fill out this table, and you guys should make a table like this on your own and follow along. Okay. So if I have two electron groups, and right now I'm showing two bonding pairs, that's what BP stands for. I have two bonding pairs here. Here's one, here's two, right? Two bonds. And I have no lone pairs. Okay. What is my electron group geometry? It's gonna be linear. Okay, you see, it's going to be straight. It's going to be linear. And what's going to be my molecular shape? Well, also linear. All right. And what's going to be the bond angle? That's going to be this angle here. Well, if things are linear, they're 180 degrees. And that's pretty straightforward. Okay, so that's what it is for 2 electron groups. Let's move on to 3 electron groups and see what that looks like. Okay, now I'm putting together the model. Can you guys imagine how you would put 3 things around a central atom so that they're as far from each other as possible? Can you imagine that? It should look like this, right? That's as far as I can put them, so that it minimizes electron-electron repulsion as far away as possible. So how many bonding pairs do I have? I got 3. Okay. I have no lone pairs. Okay, so 0. And then I consider, what is my electron group geometry? Electron group geometry, so this triangular looking thing is called trigonal planar. Trigonal because you got 3 legs, kind of like a tripod, right? Trigonal. And planar because it's flat. See how it's flat? Okay. All these atoms are in the same plane. That's why it's called that. So we're gonna put here trigonal planar. Okay. Molecular shape, also trigonal planar. Okay, and then let's think about the bond angle. What is that? This angle right here. Circle's 360, right, everyone? So you divide that in 3, that's 120. Okay. So each one of those is gonna be 120. Okay. Okay. So now we're gonna play this game, everyone, where I'm gonna rip off one of the bonds. Okay, and I'm gonna replace it with a lone pair. So here, right? That's my lone pair now, right? It doesn't have an atom. It's just 2 electrons. Okay. It's not attached to an atom. Okay. So we still have what? 3 bonding, 3 electron groups. 1, 2, 3. So we have 3 electron groups. But now we only have 2 bonds, right? 2 bonding pairs. And 1 is a lone pair. Okay. So actually, you know what? I'm gonna switch it over to, because I think this will be more visually helpful. So I'm gonna make the lone pair a little shorter. Okay. So and that's actually close to the truth because lone pairs, they lie closer to the central atom than bonded pairs. Bonding pairs have to reach out to bond to an atom, whereas lone pairs, they just stay there, right? So that's 2 electrons. Okay, so we got 2 bonding pairs and 1 lone pair. But if you look at the electron group geometry, you still see that it's trigonal planar, right? It's still trigonal planar. Okay. Okay, because you got 1 here, 1 here, and 1 here, right? And they're all spread out. Okay, but now what is the molecular shape? Well, molecular shape, how it's different than electron group geometry is, for molecular shape, we only see atoms and bonds. Lone pairs are invisible to us, right? So for the molecular shape, we're only looking at this part, right? This part here. Okay, so ignore the lone pair on top. And what do we see? It's not straight, it's bent, right? So that's called bent. And now if you think about the bond angle, right? Earlier it was 120, but as I just mentioned, the lone pair lie closer to the central atom than bonded pair. So the lone pair actually repel much more than bonding pair. So this lone pair actually pushes these 2 away, right? It pushes on these 2. So this angle is no longer 120 because it got squished, right? By the lone pair here pushing it down. So it's going to be less than 120. All right. Great thing is you just have to say less than 120. Okay. So that's what it is. Okay. Now let's continue. We're going to go to 4 electron groups now. So 4 electron groups. Think about it. How do I make 4 things bound to a central atom as far away from each other as possible? What would that look like? Now, some of you are going to want to say, oh, it's a cross. That's close, but actually you can do even better than a cross. Right? You can do this. Okay. So we now have 4 bonding pairs, right? 0 lone pairs. This shape is called tetrahedral. The electron group geometry is tetrahedral. You see tetra because you got 4, but actually it's called tetrahedral because these atoms form the vertice of a tetrahedron, the polygon tetrahedron, right? And so that's why it's called tetrahedral. And without any lone pairs, the molecular shape is also tetrahedral. With the bond angle, you guys can see it. It's actually, you see why a cross wouldn't be, wouldn't be right, because a cross has 90, right? So this is clearly bigger than 90. So the angle here is 109.5. You cannot just memorize that, okay? It's hard to calculate, but you can see it's 109.5. It's higher than 90. Okay, so we can continue playing our game. We're gonna rip off a leg, and we're gonna replace it by a lone pair. Okay, so here we go. Right, there's my lone pair. I still have 4 electron groups, right? Because 1, 2, 3, and then the lone pair is 4. Okay, the bonding pairs though, I only got 3 bonds. Okay, 3 bonding pairs, and I got 1 lone pair, so that's 1. What is my electron group geometry? Well, it's still tetrahedral because I still have 1 here, right? So it's still 4. So it's still tetrahedral. And the molecular shape, well, now remember, I can't see lone pairs in molecular shape. So I see this shape. Do you guys see how it looks like a pyramid, right? Like it looks like a pyramid, right? And it's 3-legged pyramid. And so that's why it's called trigonal pyramidal. That's the molecular shape, right? Trigonal pyramidal. Now, thinking of the bond angle, same reasoning as before. Remember that lone pairs, they repel more than the bonding pair? So originally, these were 109.5, right? As we said earlier. But this lone pair now is going to squish on these even more. So we're going to have at least less than, right? It makes sense to have less than 109.5, but it's actually calculated to be 107. So you can just remember to drop it down by 2 degrees from 109.5. It's 107. Okay. All right, let's keep playing the game. I'm going to rip off 1 more bonding pair. I'm going to replace it with a lone pair. Okay. So now it's going to look like that, right? I still have 4 electron groups, right? Because it's still 1, 2, 3, 4. Right? I still have 4 electron groups, but now I only have 2 bonding pairs. And I have 2 lone pairs now. Okay. So my electron group geometry is still tetrahedral, as you can see, right? Still tetrahedral. But the shape now, you can't see the lone pairs, so you just see this. Again, it's bent, right? You've seen this before. Bent. And what about the bond angle? Well, now you've got a second set of lone pairs that's pushing on these bonding pairs even more. So 107 goes down to 105. Again, another 2 degrees, right? So that's pretty straightforward. Just drop it by 2 degrees every time you add another lone pair. Okay. And that's it. So you guys only need to go up to 4 electron groups, no from 2 to 4, and linear to tetrahedral. Okay. Now, there's certain patterns that make this easier to memorize. So if you have, notice if you have 2 electron groups, it's always going to be linear, right? And 0 lone pair. if you have 3 electron groups and 0 lone pair, it's always going to be trigonoplanar, right? For both electron group geometry and molecular shape, right? Same here, okay? Okay. So when is it the electron group geometry and molecular shape are the same? It's when you have 0 pair. Okay. And then what's another pattern to see? Well, if you have 3 electron groups, it's always trigonoplanar. If you have 4 electron groups, it's always tetrahedral. Okay. And the molecular shape changes based on the lone pairs. Okay. All right, yeah. So best way to learn this, of course, you want to practice, right? And a lot of these problems are going to ask you to go from the beginning, from a chemical formula, and they'll ask you, okay, what is the electron group geometry and molecular shape? Okay, so let's practice. Let's practice that. Okay, so let's say you have CH2Cl2. Okay, and it's asking, what is the electron group geometry and molecular shape of this compound? Okay. The first thing you always want to do is start with the Lewis structure. Okay, so let's write the steps. Okay, step 1, always start with the Lewis structure. So valence electrons here, 4 plus 2 times 1 plus 2 times 7. That's 20 valence electrons, right? Carbon as your central atom, obviously, of these 3. And then you're going to put your surrounding atoms evenly around, right? 2 hydrogens, 2 chlorine. Single bonds only. That gives you 8 electrons used and 12 electrons left. So you're going to do like that. 12 electrons, 6 on each. Count octet. Carbon has octet, chlorines have octet, so we're good. So octet is done, okay? So that's going to be your best structure. And now from that, you're going to count the number of electron groups, right? Because that's how you're going to get electron group geometry. It's based on the number of electron groups. So count the number of electron groups around the central atom. Okay. It's always around the central atom. You do not care about surrounding. So right now, I only have 1 central atom, that's carbon. So just count the number of electron groups around it. 1, 2, 3, 4. Remember, everything counts as 1, right? Single, double, triple bonds, they all count as 1. So all these are single bonds. They're worth 1 each. So we have 4 electron groups around the carbon. So we can already say that the electron group geometry is, remember, 4, tetrahedral. Okay. And if you have no lone pairs here, right? You have 4 bonding pairs. You should count that as well. The 0 lone pair. Okay. So count the bonding pairs and lone pairs, okay, to determine electron group geometry and molecular shape. Okay. So quite simple, right? Just those 3 steps. So if you got 0 lone pair, remember the molecular shape is the same as the geometry. So the molecular shape is also tetrahedral. Okay. All right. So yeah, let's do another one. Same question, but we're gonna do CN. F3, for example. Okay. So again, start with the Lewis structure, right? Got 5 plus 3 times 7. Right. This is why we learn Lewis structure. All right. So start with that. We got 26 valence electron. N is the central. Put F around. That's 6 electrons used. got 20 electrons left, right? We're gonna distribute them as pairs from outside to inside for octet, 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. Okay. So I've used how many? That's 2, 4, 6 dots over 3 fluorines. 6 times 3 is 18. I still have 2 electrons left. I'm going to put them on nitrogen. Okay. So does everybody have octet now? Well, the fluorines do. And check nitrogen, 2, 4, 6, 8. So we're good. Okay, so that's our structure. Now we're going to count how many electron groups are around the central atom. So nitrogen, how many electron groups, everybody? 1, 2, 3 for the 3 bonds, and then the lone pair counts as 1. Remember, everything counts as 1. So 1, 2, 3, 4. We just have 4 electron groups. Okay, which means we already know the electron group geometry, right? With 4, it's tetrahedral. How do you put 4 things as far away from each other as possible around a central atom, right? Remember, tetrahedral. And now we also count the bonding pairs and lone pairs. There are 3 bonding pairs, and there's 1 lone pair. So remember how that works? Take tetrahedral, and here I'll show you guys a cool trick. You can do tetrahedral like that. See how this knuckle is the central atom, and then here's the 4 bonds, right? So this is tetrahedral, okay? If I take 1 away and replace it with a lone pair, what do I have? That's a pyramid, right? With 3 legs, so it'll be what? Trigonal pyramid. Okay, this is my molecular shape. Okay. All right. Let's do one more. Let's do H2O. Okay. This is familiar. We should know this, right? So H2O, that's 2 times 1 plus 6. That's 8 valence electrons, okay? Oxygen's going to be the central atom. Yeah. And we're going to put the hydrogens on each side and then single bonds. That's 4 electrons used. 4 electrons left. The hydrogens don't need them, so we'll put on the oxygen, 4, right? So we'll put it as pairs, okay? So now you count the number of electron groups around oxygen, 1, 2, 3, 4. So the electron group geometry is tetrahedral. And we have 2 bonding pairs, right? And 2 lone pairs. So remember how that works? Tetrahedral, okay? I got 2 lone pairs now, so I'm going to take 1 leg away. I'm going to take the other leg away. Oh, what does that look like? That's bent, right? So my molecular shape is bent, right? So it's quite straightforward as long as you have the correct Lewis structure, okay? So make sure that everything has octet, that you have the right Lewis structure, and then you just go and count the central atom, the number of electron groups around the central atom. Okay? You really don't care about the surrounding atoms. Actually, let's do one more. I want to show you guys a molecule that's more complex, like with 2 central atoms. If you were asked, right? Let's say if you were asked, what is the electron group and molecular shape for, say, CH3OH, okay? So CH3OH, remember I was telling you guys earlier, when you have a larger compound, it will be written out for you so that you can see the connectivity better. So CH3OH, we're going to have a carbon that has 3 hydrogens attached to it, right? And then that carbon is attached to the oxygen, right? You just read it like from left to right. And then on that oxygen, another hydrogen is attached, okay? You can still do valence electrons. It'd be 4 plus 3 times 1 plus 6 plus 1. That's 14, right? 7, 10, 14. So now you do single bonds everywhere. 2, 4, 6, 8, 10 electrons are used, and 4 electrons left. So where are you gonna put it? Well, the hydrogens don't need it. Carbon doesn't need it, right? Because it's 2, 4, 6, 8 already. So it's on the oxygen, but 2 pairs. Okay. So you realize, okay, this compound has 2 central atoms. Okay. So if it wants the molecular shape and electron geometry of this, it actually wants it 1 central atom at a time. So let's call this, this carbon, we need to count the electron groups, right? 1, 2, 3, 4. So for the carbon, the electron groups is 4, right? So that's going to be tetrahedral for the electron group geometry. Okay, right? 1, 2, 3, 4. And it has no lone pair. So the molecular shape is also tetrahedral. Now, you do it separately, right? You do 1 central atom first, then you move on to the next. So notice when I did carbon, I didn't care about what was going on with oxygen or anybody else. I just count the electron groups around carbon. 1, 2, 3, 4. Okay. Now I'm going to do the same thing for oxygen. Number of electron groups around oxygen, 1, 2, 3, 4 as well. Okay. So the electron group geometry is going to be tetrahedral. However, around oxygen, there's 2 bonding pairs and 2 lone pairs. Okay. So the molecular shape, right? So tetrahedral, 2 lone pairs, we are at bent. So again, when you have a larger structure with multiple central atoms, just do 1 central atom at a time. Then you can, then it's very, very, very simple. Right? It's just zoom in on the central atom and count your electron groups, count the bonding pairs and the lone pairs, and that's all you should need. All right, guys, that's it. I'll see you next time.